Welcome to this series of videos on topics in physics and math. In this video we'll be exploring dielectrics and their associated equations and variables like the polarization and displacement vectors. And we'll plug numbers into the different equations to see what the typical values are for these variables. To get a better idea of what these variables describe, I've drawn up a picture of two charged metal plates. They are separated by a distance d, which isn't important right now. What is important is to get a sense of the variables described. E0 is the electric field between the plates with no dielectric material in between, but only having air or a vacuum. Air is very nearly the same as a vacuum in terms of its dielectric quantities. E0 is called the external electric field. Here are the quantities of electric field when a slab of dielectric material is put in between the charged plates. An electric field is induced in the material due to the charge on the electric plates. Since positive and negative charges are induced in the material, this electric field is called EP, or the induced electric field. It is defined to be positive in the same direction as E0, so when it's in the opposite direction, it is negative. Adding the two fields together gives a resultant electric field in the material called ED, or the electric field in the material. This is the field that is felt by charges that can move freely in this dielectric material, and is an important quantity here. There is an equation at the top relating the three quantities. Here are a set of equations relating many of the quantities together. It is important to notice here that the displacement vector D is equal to the electric field in the material ED multiplied by a fundamental constant, epsilon 0, which is the permittivity of free space. So D is just another way of writing ED. Similarly, the polarization P is just another way of describing EP, and the variable chi E, which looks like a curly X with a subscript E, is defined to be the ratio of P to E0 times epsilon 0. Many physics textbooks neglect to put the E in, but I'd like to do so I can contrast it with its magnetic equivalent chi M. Similarly, kappa E, which looks like a curly K with a subscript E, is the ratio of D to E0 times epsilon 0. I've used the subscript E here for a similar reason as for chi E. Note that there is no value for epsilon 0 times E0, even though there should be. Maybe it only complicates the math. I'd like to derive a few more equations from these so as to get you used to using them and build familiarity with them, because they can become confusing. Firstly, I'm going to derive this expression for D, which looks like a definition, but can be derived from the other expressions. By using these three expressions and substituting some into others, I can easily derive this one here, which is what chi E is in terms of kappa E. The equation looks very simple, but it does serve a purpose. I can now use this one to derive others. Here is another expression I can derive. It also looks like a definition. So kappa E is also the ratio between these two electric fields and can be used to calculate the capacitance that uses these two charged plates. Here is a derivation of P in terms of D and kappa E, which is a way of getting the value of P without ever needing to know the external electric field. Here is a similar derivation of P in terms of D and chi E. Here are some typical values for different quantities. Epsilon r is in the same order of magnitude for most of these materials. I chose these materials because they seem to have strongly consistent values. Here are some values for kappa E for the same materials. I chose to get the reciprocal because ED must be smaller than E0. I've also listed the permittivity of these materials. Here is a list of the values of chi E for the same materials. Notice that these values are negative since P is in the opposite direction to E0. I'd like to get typical values for P and D in a standard capacitor. I'll start with E0 inside a capacitor between its two rolled up plates. Notice that the capacitance of the capacitor makes no difference, only the voltage, choice of materials, and separation between the plates. The separation of the plates can be guessed to be 1/10 of a millimeter. Using typical values for a capacitor, the displacement D can be calculated, and this is its value in any typical cylindrical capacitor. Here are the values for P and D in the same capacitor. Notice that P is negative because it is in the opposite direction to D. Here are typical values for the electric fields inside the same capacitor. Even though there is no name for epsilon 0 times E0, I thought that a good name would be D0 because it is the displacement vector in the presence of a vacuum. Here is what its value would be in this typical capacitor. Here I've shown the checking that these values are correct after I've plugged them into the equations.